This is Unit 3, Day 5B of Algebra 1. If you would like to see the warm-up or review question or any of the homework questions we went over in class today, just look at the finish notes. So today we're going to talk about some other types of functions. We're going to talk about something called piecewise functions. And then we're going to talk about how to graph functions using things called transformations. So what if we took a graph and moved it up or down or left or right or reflected it? So flipped it over the x-axis or flipped it over the y-axis. So the first type of function we're going to talk about are piecewise functions. So notice it's kind of obvious why they're called piecewise function because they're going to come in pieces. They look scary, but all you're actually going to do is you're going to graph them one piece at a time. So for one, our two pieces are f of x is equal to piece 1 is going to be negative 2x minus 1 as long as x is smaller than or equal to 2. And then our second piece is going to be f of x, or our y is going to equal negative x plus 4 as long as x is greater than 2. And what we're going to do is we're going to graph both of these by using a table. So let's start with the first one, negative 2x plus 1. Let's make a table for it. And it's telling us that x is smaller than or equal to 2. So 2 is going to be in our table because that's our boundary number. So that's going to be where our pink function is bounded up until. So if x is 2, what's y going to be? So we're just going to take 2 and plug it in. So it would be negative 2 times 2 plus 1. So that would be negative 4 plus 1, which is negative 3. Now I want numbers that are smaller than 2 because it's x is less than or equal to 2. So a number that's smaller than 2 is 1, so we'll try 1. If I take 1 and plug it in, I would have negative 2 times 1 plus 1, which would be negative 2 plus 1, which is negative 1. And then let's do one more point just as to make sure that we're on the right track. So let's do 0 because that is less than 2. So it'd be negative 2 times 0 plus 1, which is 1. So now let's graph those. So we have the point 2, negative 3. We have the point 1, negative 1. And we have the point 0, 1. Now notice those points exist as long as x is less than or equal to 2. So here's 2. So this part of the graph is going to exist as long as x is less than or equal to 2. So it's going to look like that. I'm not going to go on the other side because if I started going over here, those are for values of x that are bigger than 2. And it told me in the problem to stop at x is 2. So now the other part of the graph, the blue one, is going to tell me what the right side of the graph is going to look like. So we have negative x plus 4, and then as long as x is greater than 2. So again, I'm going to use 2 because that's a boundary number, so I'm going to use 2. And if I take 2 and plug it in, I'd get negative 2 plus 4, which is 2. And now it's telling me to use numbers that are bigger than 2. So a number bigger than 2 would be 3. So what happens if I plug in 3? It'd be negative 3 plus 4. Again, I'm plugging in into negative x plus 4 right now. And so I would get 1. And then do one more test point. So I'll try 4. So negative 4 plus 4 is 0. So I have the point 2, 2. So 2 over, 2 up. But for this one, I'm going to do something called an open circle. Why am I using an open circle instead of a closed circle? Because it's just x is greater than 2. So if it's greater than 2, but not equal to 2, when you graph, you make an open circle. And then on this one, since it was less than or equal to 2, that's going to be a closed circle on the graph, showing that it can actually equal that number. So at 2, 2, I'm going to have an open circle. Then 3, 1. And then at 4, oops, I went the wrong way. 3, 1. And then 4, 0. So now that part of the graph is going to look like that. So that's my piecewise function. It has two different pieces that make up the function. Let's look at another one. Let's look at the one next door. So this one has 3 pieces. It's saying that f of x is negative 4 as long as x is less than or equal to negative 2. And then it's saying that f of x is x minus 2 as long as x is in between negative 2 and 2. And then it's saying that f of x is negative 2x plus 4 if x is greater than or equal to 2. So let's look at the pieces of this graph. So let's look at the green piece first. So it's saying that f of x, which is y, is always equal to negative 4 as long as x is less than or equal to negative 2. So let's do negative 2. It's saying the y value is always negative 4. And then smaller than negative 2 could be negative 3, and then negative 4, and then negative 4, negative 4. So this is going to be negative 2, negative 4, negative 3, negative 4, negative 4, negative 4. And then notice it's less than or equal to, so that is going to be a closed circle on the graph. And since it's smaller, I'm going to move to the left. And so that's going to be what the green piece of my graph looks like. Now the purple piece, we have x minus 2, and it's between negative 2 and 2. So I'm going to use negative 2 and 2 are both boundary numbers, so I'm going to use both of them. And then I'll use a point in the middle, so I'll try negative 2. If I take negative 2 and plug it in, I would get negative 2 minus 2, which is negative 4. If I take 0 and plug it in, I get negative 2. And if I take 2 and plug it in, I get 0. Notice both of these are going to be open circles because it's just less than and not equal to. So negative 2, negative 4 is an open circle. And you know what, gentlemen? I graphed this at positive 4, so let's graph that appropriately. Let's go down, and it would be negative 2, negative 4, negative 3, negative 4, negative 4, negative 4. It'd be down there, not up at positive 4. So now for my purple one, negative 2, negative 4, it's already there, so it's already filled in, so we're good to go. And then 0, negative 2, and then 2, 0. And so this one is going to exist here. And then on that last one, it's supposed to be an open circle. So at 2, 0, it should be an open circle. And it goes like this. Now at negative 2, negative 4, since the green function already filled it in, it doesn't need to be an open circle anymore because it's filled in. And now we have our last piece, which is negative 2x plus 4, as long as x is greater than or equal to 2. So it's greater than or equal to, so this one's going to be a closed circle. So if I plug in 2, I get 0. If I plug in 3, I get negative 2. And if I plug in 4, I get negative 4. So 2, 0. Oh, now I get to fill in that circle. And then 3, negative 2. And then 4, negative 4. And so this one's going to look like that. So that graph has 3 different pieces, but they all end up connecting. So those are just some examples of piecewise functions. So you guys go ahead and graph this piecewise function, so you can pause the video and try, and then you can check your work against the finished notes from class today. So go ahead and pause the video and try and graph that function. All right. So moving on from our piecewise functions, let's talk about some common parent functions. So a parent function is just the most basic version of a function. So it's the most basic version of the function or equation. So for instance, y equals x squared is the most basic version of x squared. I didn't multiply it by anything. I didn't add anything to it. So it's just y equals x squared. And we've graphed this a couple times, but let's go over it again. So if I have negative 3 and I square it, I get 9. If I have negative 2 and I square it, I get 4. If I have negative 1 and I square it, I get 1. 0 squared it, and I get 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. So I have the point 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, 3, 9, negative 3, 9. And then notice it just makes a happy parabola. So that's the parent function y equals x squared. Another common parent function, do you guys remember doing this one, the absolute value of x, what this one would end up looking like? So if we take the absolute value of negative 3, we get 3. The absolute value of negative 2 is 2. The absolute value of negative 1 is 1. The absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. Absolute value of 3 is 3. So we have 0, 0, 1, 1, negative 1, 1, 2, 2, negative 2, 2, 3, 3, negative 3, 3. So it almost looks like the parabola, but instead of curving, you make straight lines. So the parent function for the absolute value looks like a v. All right, let's do the square root of x. I think that we did this on the first day as well. So the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. And the square root of 16 is 4. So we have 0, 0, 1, 1, 4, 2, and 9, 3. And then the 16 would be off the graph. So he kind of looks like half of a sideways parabola. So that would be the parent function for the square root function. So we've got 3 different parent functions that we've talked about now. So we have the x squared that looks like just a u. We have the absolute value function, which looks like a v, and we have a square root function that looks like half of a sideways parabola. So let's talk about moving these guys. So let's compare the graphs of x squared plus 2, and x squared minus 3. Let's compare those graphs on Desmos. So you guys should have downloaded Desmos at the start of the year. So let's go ahead and pull up Desmos and graph it. So we have y equals, and then x squared. So notice we have our happy parabola there. What do you think is going to happen if I do y equals x squared plus 2? What do you think is going to happen to the parabola if we do that? So if we add 2, what happened? What's the difference between the blue graph and the red graph? The blue graph moved up how many from the red graph? It moved up 2. So when you add 2 onto the end of your function, that shifted the whole graph up 2. So we had our happy parabola, and I'm just going to sketch this. So that's our x squared parabola. And then if we took the x squared plus 2 parabola, it took that happy parabola and it moved it up 2. What do you think now that the x squared minus 3 is going to do? So y equals x squared and then minus 3. If we took that parabola and subtracted 3, the green parabola, the x squared minus 3 parabola, shifted 3 down from the x squared parabola. So if you take your equation, x squared, and you subtract 3 from it on the graph, it's going to move the entire parabola 3 down. So 1, 2, 3. It shifts that entire happy parabola 3 down. And there we go. So those are called vertical shifts. So if you add or subtract to the entire function, it either moves the parabola up if you're adding, or it moves it down if you're subtracting. So why don't you guys go ahead and see if you can do these two guys. What happens if you take the absolute value of x plus 1? And what happens if you take the square root of x and subtract 4? So take a minute, pause the video, and see if you guys can sketch each of these graphs based off of the parent function. Okay, we know that the square root of x from up above looks like a v. If I add 1 to that, that's going to move that entire graph up 1. So it's going to shift that entire graph up 1, and then it's just going to be the v graph, but moved up 1. The square root of x minus 4, well, from up above, we know the square root of x graph looks like half of a sideways parabola. If we subtract 4 from it, it's going to move the entire graph down 4. So 1, 2, 3, 4. It's going to take that sideways parabola and just move it down 4. So it'll look like that. Horizontal shifts. So let's say we want to take that x squared graph. So we know x squared is that happy parabola. So let's just make our original guy, the green guy. What do you think the x plus 2, if I put that in parentheses and square it, or x minus 3, if I put that in parentheses and square it, what do you think that's going to do to our parabola's graph? So let's go on Desmos and see. So we have our original parabola, and now it's saying to do y equals x plus 2, and then square it. Oh, what happened there? So we had our red parabola, which was x squared, and now our purple parabola is the x plus 2 squared. Which direction did it move when I did x plus 2? It moved it 2 to the left. So that x plus 2 on the inside moves it 2 to the left. That's interesting because I'm adding 2. You would think that that would move it 2 to the right. But when it's inside, it makes it x plus 2. That moves it 2 to the left. So based on that, what do you think is going to happen if I do x minus 3 squared? Which direction do you think it's going to move my parabola? So x minus 3 squared, that parabola, the black parabola, is the x minus 3 squared. That moved it 3 to the right. Interesting. So if I'm going to do these two new parabolas, so the x plus 2 on the inside moved it 2 to the right. So it's a happy parabola, but just moved 2 to the right. And then if I do x minus 3 squared, that's going to be a happy parabola, but it moved 3. Sorry, the pink parabola moved 2 to the left, and the brown parabola moved 3 to the right. So now using that information, see if you could sketch each of these graphs. This absolute value of x minus 5, what would that look like? And then the square root of x plus 3, what would that look like? So go ahead and pause the video and see if you guys could do these two. All right, the absolute value graph parent function looks like a v. And then remember, if it's x minus 5 on the inside, that's going to move it 5 to the right. So we're going to take that happy parabola. We're going to take that v and move it 5 to the right. So 5 to the right, and then we're going to make our v. The square root parent function looks like half of a sideways parabola. And then since it's x plus 3 underneath the square root, that's going to move it 3 to the left. So 1, 2, 3, and then it's going to be the sideways parabola 3 to the left. Reflections. So those are like mirror images. So for reflections, we're going to flip over the x-axis or y-axis. So what is that going to look like for this? So we have the square root of x, the opposite of the square root of x, and the square root of negative x. What do you think, which way are they going to flip based on those two things? So let's see. So our parent function is y equals the square root of x, and there we go, our half of our sideways parabola. What's going to happen if I toss a negative in front of that? Let's find out. Oh, it took the red square root function and it flipped it over the x-axis. So this flips it over the x-axis. So it's an up and down reflection. So it's a reflection over the x-axis. So it flips it from up to down. What do you think if I put the negative on the inside of the square root, what's that going to do? So the square root of negative x. Oh, that's going to be the green one, and that flipped it over the y-axis. So when the negative sign is underneath the square root, that's going to flip it over the y-axis, or it flips it from the right side of the graph to the left side of the graph. So let's go ahead and sketch those in. So our original function, the square root of x, is just half of a sideways parabola. And then if I do the opposite of the square root of x, that's going to flip that's half of a sideways parabola, and it flips it up, down, so it's going to flip it over the x-axis. And then if I did the square root of negative x, it's going to reflect it over the y-axis, so it flips it over the y-axis. So go ahead and now, using that information, see if you can sketch each of these guys. What would it look like if you did negative x squared, and what would it look like if you did the absolute value of negative x? So pause the video and try those. All right, on the A, our normal parabola, x squared looks like that. And then if I did negative x squared, that's going to flip it over the x-axis, so it flips it from up to down. And so that's going to look like a sad parabola. If I did the absolute value of x, that's the v. And then if the negative's on the inside, it flips it over left to right. And so if I flip it over left to right, it's going to look identical to the original problem. So it doesn't actually change the original graph at all. If I did the absolute value of negative x, or if I did the absolute value of x, it looks the exact same in both of those situations. All right, so let's put some of the transformations together. So on A, I have negative x squared plus 1. More than one transformation happened. So my original graph is x squared, so it's a happy parabola. Two different things happen to this parabola. What does that plus 1 at the end do to the parabola? It moves it up 1. What else happened to the parabola? It has a negative in front of the x squared. When it has a negative in front of the x squared, it's a reflection. And then remember, if it's in front, it reflects it from up to down. So it reflects it over the x-axis. So this is going to be a parabola. I moved it up 1, and then it's reflected up, down. So it's going to be a sad parabola. It's going to go over the x-axis. On B, several things are happening. So my parent function, it's absolute value, so my parent function is going to be a v. What happened to this v? Well, right here has a plus 3 on the outside, so that's going to move the entire absolute value graph up 3. And then we have an x minus 4 on the inside. Remember, when it's on the inside like that, x minus 4, it's going to move it to the right 5. So we went up 3 and to the right 5. And then that negative out in front, it's another reflection. And since it's out in front, it's going to reflect it from up to down. So it's going to be a v that's going down. So I'm going to go up 3 and then to the right 5. 1, 2, 3, 4, 5. And then my graph moved to the right, oops, not 5, 4. So it moved to the right 4, and it moved up 3. I don't know why I put 5, it should be 4. And then it's going down because it's reflected. So it's a v that's going down that moved up 3 and to the right 4. All right, gentlemen, your homework is 3.8. Let me know if